Hi, this is Dr. John Bergduff. In this video, we're going to back up a little bit and look at multiplying and dividing simple numerical fractions. Now, the purpose for this is we're going to eventually need to talk about multiplying and dividing rational expressions, fractions that contain variables in them. But often our difficulties with that more complex topic come from the fact that we need to build our understanding a little bit stronger about just multiplying and dividing basic fractions. So this is going to go way back to basics and explore how we multiply and how we divide two fractions. Let's start right away. Suppose I want to look at the multiplication problem, 1/2 times 1/3. Now, you probably know the rules, and so put those aside for a moment, and I just want to explore where this might come from. In mathematics, for example, in word problems and other applications, the word the operation of multiplication often can be related to the word of, so that 1/2 times 1/3 can be thought of as 1/2 of 1/3. Now, if you do that, it's easy to illustrate what 1/2 of 1/3 would be in a picture, and then that will help you understand how to multiply the two fractions. So here we have a circle that's divided up into thirds, and suppose we want to take 1/3 and take half of that. So let's start by considering one of the 1/3. There's a third. And I want to take half of that. Well, I could do that mathematically rather simply by just taking that region and cutting it in two pieces and only taking one of those pieces. And then asking yourself, well, how much of the circle do I have now? As is, that might be hard to see because all the pieces now are different shapes. However, if we take the vertical line and extend it, and the diagonal line and extend that, we see that really what we've created is 6 pieces all of the same size, and what I have in red is one of those 6 pieces. So 1/2 times 1/3, or 1/2 of 1/3, is 1/6. And notice that 1/6 is simply 1 times 1 in the numerator and 2 times 3 in the denominator. I didn't find a common denominator there, not necessary. Let's explore this idea a little bit more carefully. Suppose our calculation that we want to do is a little bit more involved. Suppose you have 3/4 of 2/5, or 3/4 times 2/5, giving it away here. That's multiplication symbol. And again, I want to think of that as 3/4 of 2/5. Now, creating circles to represent fifths and then fourths of that is a little bit more complicated, so I want to show you a way that I think works rather well. Imagine instead of a circle, your whole is represented by a rectangle. And I want to start with 2/5, so I want to take my rectangle and imagine that I'm dividing it into 5 vertical rectangles, 1, 2, 3, 4, 5. So I've divided my entire rectangle into fifths, and I want to take 2 of those vertical bars to represent 2/5. And I need to try to picture, how do I take 3/4 of that? Well, instead of dividing the rectangle into vertical bars, imagine we divide it into 4 horizontal bars, like this, and taking 3 of those. So the 2/5 is the red, and I'm going to represent 3/4 in green. So I'm going to go like this. And then I want to look at the 3/4 of the 2/5 would represent the area that I have shaded in both colors. That would represent this. And notice that as I subdivide my rectangle both vertically and horizontally, I've created a lot more parts to my rectangle. Let's count how many there are. So there's 1, 2, 3, 4, 5 in each row and 4 rows. So that makes a total, I believe, of 20 sections of that rectangle. And what I have selected as having colored in both colors, what I've sort of re-outlined in the gold there, is 6 of them. So 3/4 times 2/5 is 6/20 by the picture. And you can see that what we've done there is we've multiplied the 2 numerators and we've multiplied the 2 denominators. Again, we did not need a common denominator for this, which we do in addition and subtraction. You might remember that that was pretty involved. With multiplication, you do not. Now, you might ask, whoops, that fraction can simplify. Should I simplify it? Yes, let's make an agreement that all fractions should be simplified. So when I look at the 6/20, I recognize that the 6 is 2 times 3, and the 20 is 2 times 10, so that the 2's will divide out. 2 divided by 2 is 1, and I will be left with a result of 3/10. That would be my final answer. But the key thing I want to note here, and having illustrated with 2 different diagrams, is the following definition for how you multiply fractions. So first of all, in symbols, suppose that A, B, C, and D are all integers, and that the B and D are not equal to 0. That's so you're not dividing by 0. Then the product of A over B times C over D is A times C over B times D. And saying that in words, what we've done is this. To multiply 2 fractions, multiply the numerator by the numerator and the denominator by the denominator, and that's all there is to it. That's how you multiply fractions. Now, hopefully with that foundation really well established, and remembering that we do not need common denominators for multiplying fractions, let's do a little bit more complicated example with some uglier numbers, and just make sure that we feel confident in this. Suppose I want to multiply 9/35 times 14/15. Now, according to what we just saw, we'll multiply the numerator by the numerator and the denominator by the denominator. And you might immediately say, ooh, those are some kind of big numbers. And considering especially that we want our answer finally ultimately simplified, working with those big numbers is not going to be a lot of fun. So here is what I recommend. Before we actually do any multiplication, let's factor all of these numbers and see whether we can find any simplification like we did on the example we just did. So let's factor everything. 9. 9 is 3 times 3. 14 is 2 times 7. Then going into the denominator, 35 is 5 times 7. And 15 is 3 times 5. So I factor everything. And when I do that, I realize that I see common factors between the numerator and denominator that can be divided out. Definitely what you want to do. Let's take a look for those. I see a 3 in the numerator that could divide with the 3 in the denominator. There'd still be a 3 left. Only one of them can divide out. I also see a 7 in the numerator that can divide a 7 in the denominator. And once I divide out those common factors, multiplying what remains is really not a big problem at all. Far easier than dealing with the way the numbers originally were. So in the numerator you have 3 times 2 is 6, and the denominator you have 5 times 5 is 25. And if you've done all that carefully, you shouldn't have to simplify any further. Again, notice we did not need a common denominator at all. So that's multiplication. What about dividing? Now, dividing fractions is a little bit harder to illustrate. I'm going to try to use something called the missing factor approach. And this will be easiest to understand if I start with an even simpler example. So let's go way back and think about how do you divide 6 divided by 3? And we all know the answer to that. But the way you may have been shown this when you first saw the concept of division is to say this. Suppose 6 divided by 3 is, I don't know what. We'll call it a box. What 6 divided by 3 is the number which, when you multiply it by 3, would give you 6. So when you want to say 6 divided by 3, you ask yourself, what do I multiply by 3 to get 6? What is the missing factor? And then this, you can plainly see, would be a 2, and that shows you that 6 divided by 3 is 2. What do you multiply by the second number to get the first number? Now let's try that with some fractions, which will look a little bit more painful. Suppose I want to divide, let's see, 2/3 divided by 2/5. And we wonder what that is. Well, very much like the operation we just did, we ask ourselves, what, I make the box a little bit bigger here just because I've got to put a lot of stuff in it. What do I multiply by the 2/5 to get 2/3? What do I multiply by 2/5? What do I multiply by the second number to get the first number? Notice the similarity there. And then I have to figure out what goes in the box. And you might say, oh, that looks a lot more complicated. So I'm going to do something that looks slightly like cheating, if you don't mind. What I'm going to do in trying to figure out what I can put in the box to make this true is I'm going to do this. Well, I know eventually that the product I want to reach is 2/3. So what if I at least start by putting a 2/3 in the box? Well, 2/3 times 2/5 is certainly not going to be 2/3. I wish that 2/5 were not there. Let's do this. Suppose that also in the box you put a second fraction, and that fraction I create by taking my 2/5 fraction and flipping it upside down. Because you notice if I do that, that this 5 would divide that 5, and this 2 would divide this 2, and you truly would end up with 2/3. Well, that may seem a little bit like cheating, but that is what would go in the box, and therefore that's the result of the division. Now let's look at what we have a little bit more closely, because there's a cool word we can use for this and a simple idea. When you look at 2/3 divided by 2/5, what happens, what goes in the box, is you still have the 2/3 to begin with, but then you take that 2/5, that second fraction, and you basically flip it over. That creates what is called the reciprocal of the fraction, which simply means take the fraction and flip it over. Numerator becomes denominator, denominator becomes numerator. And although that's a little fancier than the picture with the circles and the rectangles, it does inspire the rule or the definition for how we divide fractions. So in this one, let A, B, C, and D be integers. B, C, and D, none of them can equal 0. You'll see that you would be dividing by 0 somewhere if that were allowed. How does this work? A over B divided by C over D is equal to A over B times D over C. Notice that what we do here is we take the second fraction and we flip it over. Then once the division problem is converted to a multiplication problem, we simply multiply the two numerators and we multiply the denominators. Now in words, which is probably a little bit easier to work with, to divide two fractions, you multiply the first fraction by the reciprocal of the second fraction. Multiply the first fraction by the reciprocal of the second. So that's the origin of that definition, which we're familiar with, but knowing where it comes from, I'm hoping will be a positive thing. Let's look at a couple of examples of this to make sure that we're okay. So suppose we want to divide And what I want to divide is 22 over 25, 22 25ths, divided by 33 20ths. Now, when you divide, the very, very, very first thing you do is you take the first fraction as it is, and then you multiply by the reciprocal of the second. So the division becomes a multiplication, and the second fraction, you look at its reciprocal. In other words, you flip it over. Now your division problem has automatically changed into a multiplication problem, and basically we can follow the rules we already knew. Once again, these are large numbers, so we're better off if before we actually try to do any multiplying, we factor everything. So looking at 22, you might notice that that's 2 times 11. And below that, in the denominator, 25 is 5 times 5. 20 is 2 times 10. But if I think about it, 10 is 2 times 5. So 2 times 2 times 5. I'm factoring it as far as I can. 2 times 2 is 4 times 5 is 20, looking at it a different way. And 33 is 3 times 11. Now notice that I am not writing these two fractions together. I certainly can. If you look back to the example of multiplication I did earlier, I immediately took the two fractions and wrote them as one. And you can do that here. But you can also leave them separate, because what's going to happen is eventually you are going to multiply all the factors in the numerator and all the factors in the denominator. So any common factor you see in any numerator that would divide out the same common factor in a different denominator, that's okay. That would work just fine, because eventually they all go together. So for example, seeing this 11 here in the first numerator and the 11 in the second denominator, they will divide out. 11 divided by 11 is 1, because eventually they will be in the same fraction. Anything else divide out? Yes, there's a 5. This 5 divides one of these two, just pick one of them. And then the multiplication reverts to simply multiplying what remains, which is a lot easier. In the numerator, you have 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. In the denominator, 5 times 3 is 15. 8/15. That's how you divide those fractions. How about one more, just to be safe? In this one, I want to throw in a negative number. Not that that really changes anything, but just for discussion's sake, negative 18 over 21. And I also want to show you that if one of your numbers is a whole number, that works out okay too. So negative 18 21st divided by 6. Okay, now here's the problem. We've been talking everything about fractions, and the second number is not a factor. It's not a fraction. That's okay. Any whole number can be changed into a fraction by simply writing it over 1. So 6 is the same as 6 over 1. And then dividing by 6 over 1, now we can see the reciprocal easily, is the same as multiplying by 1 over 6. Change the division to multiplication and take the reciprocal of the second fraction. Once again, don't start multiplying right away. The numbers will get too big. So let's do a little bit of factoring. When I look at the 18, what I might notice is, even without factoring this all the way into prime numbers, I notice that that is actually 3 times 6. And I could factor it farther, but if I'm looking ahead to the second fraction, I'll notice that the 6's are going to divide out. I could go ahead and factor farther, but I'm seeing that it's going to divide. The 21 in the denominator in the first fraction, that's 3 times 7. So that's kind of nice. Let's see what's left. The 3's would divide out. Actually, that tells me that the original fraction could have been simplified first. And also the 6 from this numerator divides the 6 from that denominator, because again, they'll eventually all be one fraction. What's left in all that? Well, all that's left in the numerator, I still have the negative sign by the way, is a 1, and all that's left in the denominator is a 7. The answer is negative 1/7. Now, this may or may not be useful to you, but over the years, people have come up with a couple of poems to help you remember the rules for multiplying and dividing fractions. If you like these, use them. And if you think they're silly, just ignore them. So the first one goes like this. To multiply fractions is no problem. Multiply top to top and bottom to bottom. And that's just saying that to multiply fractions, you multiply the two numerators and you multiply the two denominators. Here's one for the second one, for division. To divide two fractions, don't be shy. Flip the second and multiply. And that's just saying take the first fraction by the reciprocal of the second. So if you like these poems, if they help you remember, use them now and use them also when we talk about multiplying and dividing rational expressions later on. Hope this is helpful. Take care.